Carlo?
Yeah. So we can start the experimental session. We have 3 talks today, and I will alert the speaker 5 minutes before the end of the allocated time. So the first one is about the magnetic conversion detectors from Aldo Ejlli. And Aldo, you can start if you want to.
Yes, can you hear me?
Yes.
And then Carlo, thank you. Now, sure. Can you see the slides?
Yes.
Sounds good. Great. Yeah, hello everyone, and thanks very much to the organizer for the invitation. I am Aldo. I'm working from in the Cardiff University, and today we'll be talking about some detector concept based on magnetic conversion, actually gravitational wave converted to photons. So let me try to introduce you in this this plot where we have most of the community that are concentrated at low frequency gravitational wave as the LIGO, Einstein Telescope, LISA, International Pulse and Timing Array. I will be mostly talking about the inverse Gertsenshtein effect that are frequency, very high frequency, optical frequency and X-ray frequency. And last, so I will introduce a laser interferometry experiment that we are building here in Cardiff, and what that will be also sensitive to high frequency gravitational wave up to megahertz. So the idea behind the inverse Gertsenshtein effect is really simple in its way. So you need a source. That source is represented here by this black say sphere, emits some gravitational wave propagating the magnetic field, and the magnetic you can generate some photons through the propagation to magnetic field and can detect by a photon detector. So we know how to detect photons. This is the best way, ideally, how to see the signals through this conversion. So sources, yeah, this is called was the inverse Gertsenshtein effect. So Gertsenshtein in 1962 studied the reverse process where you generate gravitational wave by sending a laser light through a magnetic field. So sorry. Sources today, yeah, are inherently speculative at this moment, and we'll be talking about sources like black hole collision in higher dimensional gravity. So in string theory, you might heard that gravity is very strong in the 5th dimension, and here the universe is represented by one of this plane, where is the visible plane that is 3 + 1 dimension, and the gravity is very strong in between them. Any perturbation, let's say, of gravitational wave like black hole collision will make oscillation between the planes and generate high frequency gravitational wave with a higher amplitude, since the gravity is very strong. Other sources that can fall in this region of ultra high frequency gravitational wave can be also primordial black holes that have evaporated in the early universe. So I'm talking about masses below 10 to the -8 gram. This primordial black hole evaporated due to Hawking radiation, and triggering them as they generated ultra high frequency gravitational wave as a background in our universe today. Also, we saw that early universe, we have also cosmological sources. And another source we can be also our nearest star is the sun. The sun in its internal has a hot plasma, and the propagation of this plasma through fields and collisions can generate also a gravitational wave. So experimental, let's say, devices that can detect, can be sensitive to this frequency region can rule out this theory, or can also propose new fields. So the gravitational wave propagating static magnetic field, we simplify the system. So we used, let's say, this principle of graviton-to-photon conversion to compute the first upper limits in this high frequency region where a gravitational wave propagates through an orthogonal magnetic field. And then you have a generation of the photons. These photons obviously will interact with other photons of the magnetic field, virtual photon magnetic field, and then be collected by CCD. So if we write, let's say, the Lagrangian for the gravitational wave and electromagnetic wave, and assume that we are in vacuum, we don't have plasma, so everything is somehow in ideal condition, we can compute the converted electromagnetic flux of photons that are converted, and this flux depends obviously on the magnetic field square, the propagation along the magnetic field, magnitude of the characteristic magnitude of the gravitational wave squared, integrated over the bandwidth. On the other side, if we put the CCD, we can compute the flux that the SCCD or the photodetector measures, and usually these photodetectors in zero, let's say in dark, they measure a number of photons per unit of bandwidth. So having these two fluxes, let's say the generation and the detection, we can constrain what is the minimum characteristic, the amplitude that can generate that equivalent noise that the CCD and the dark measures. And as you can see here in SI units, we have this characteristic amplitude that depends on number of photons, their cross-section, magnetic field, length, and bandwidth of the photodetector, and its quantum efficiency. So where we can use such simple system, and one of ideal places is axion search experiments. So they generate axions by propagating the light through a magnetic field. These axions propagate since they are weakly interacting with the normal matter, and they pass a wall. This is called the wall, an optical barrier that stops the light, but they pass through and they reconvert again into photons. So these axion experiments has been built, prototypes like the ALPS II experiment, that they use magnetic field, that is a dipole magnet oriented along one of the reference axis, and they use this first part, for example, to generate axions, and let's say in second part to detect them. What they exclude any detection. So is a good place where we could use their data to constrain the high frequency gravitational wave, for example, in their frequency regime, for example, optical. Other experiments that we looked into, it was Oscar, same concept as ALPS. The difference here is that they used longer magnets, and these magnets were provided by the CERN magnet, and same concept. The other experiment is the helioscope experiment, where you have one of these blue magnets that are from CERN that are mounted in a movable platform that can trace the sun. So because they wanted to see axion conversion in the core of the sun. If we neglect, let's say, the axion conversion, all these detectors are suitable for constraining, let's say, gravitational wave coming from the sun or coming from a stochastic background. So here was our original idea that we worked, Michael Harmut, Grote, and I, and Gianpaolo Pisano worked on. So we neglect the generation of axions. We just focus on the detection part, since they have excluded any physical detection. We use this detection part to place upper limits. So what are the suitable sources? Since they can't point deliberately to the emitting source, we thought that the suitable source should be a stochastic isotropic Gaussian gravitational wave that is coming through all directions. And in this way, you simply can assume that the gravitational wave is orthogonal to the magnetic field, and This might come from primordial black holes, for example, and also for the fact that the cast can point to the sun, we might be able to put upper limits on the gravitational wave coming from the sun. So we collect all the data and also the main parameter that was the dark count of the photodetector, the number of photons that are detected per unit of time. And yes, having the parameter for the detectors like cross section, magnetic field length, and frequency, bandwidth, and quantum efficiency, we were able to put, let's say, the first upper limit. As you can see here, these upper limits are at high frequency, let's say optical frequency with these 3 experiments, and the best upper limit is Oscar, because Oscar used these CERN magnets where you have a high field of 9 Tesla and it's longer. And for that reason, it's better than with respect to the others. And on the other side, we have CAST, where we exclude, let's say, presence of stochastic gravitational wave background at frequency standard to 10 to the 18 Hertz. So if we see this upper limit by its own, it's just, let's say, an exclusion plot on the amplitude of characteristic amplitude of gravitational wave background, but we might need to compare it with some sources that emits. So here we have also plot here I have plot the stochastic gravitational wave background that primordial black hole might have generated through Hawking radiation for masses 10 to the 4 gram and 10 to the 8 gram, assuming a density parameter of 10 to the minus 5. Obviously, this peak emission of gravitational wave depends on the masses of the primordial black hole. And here is an assumption of what might be the gravitational wave amplitude of let's say, of gravitational waves produced by the sun. As we can see, these are orders of magnitude from meaningful, let's say, have meaningful sensitivity to rule out these models. And the big question now is where to next? So what are the perspectives towards this direction? And I want to start here with this minimal characteristic amplitude to let you focus a little bit more. So we need, let's say, higher fields, as you can see. So bigger is the field, more sensitive are you have only amplitude. And the longer is the field, is better. So to concentrate the line fields in magnetic fields, you can concentrate in a very small area. If you increase the area, obviously these line fields are not more concentrated. So you have a relation between maximum field that you can obtain for a cross section. So usually what the experiments does is just to have smaller cross section in order to reach more Tesla in the field. And we need also longer magnets. And obviously, the thing that is important also is the photon counting, the single photon detector. And putting all together, we see that there is a synergy between axion search and high frequency gravitational wave. And then we just look to the future laboratory axion experiment like ALPS II and JURA and IAXO. JURA will be a successor of ALPS II, is a conceptual design. Also IAXO right now is a conceptual design. So ALPS II is under construction, and Axel Linder in the next talk will be talking about its potential to high frequency gravitational wave and all technical details. So ALPS II is under construction. As I said, they use arrays of magnets of 120 meter magnets for generation of axion and 120 meter magnet for reconversion of these axions. And they use a Fabry-Perot cavity. Instead, IAXO will have also a higher field and a higher cross section for looking at solar axion from the sun.
Это не он там.
Yes, the problem now, what about the cavities? So
Вижу, да.
we have these cavities in the ALPS II, so we might rethink a little bit more what happens to graviton-to-photon conversion in cavities, since they are using Fabry-Perot cavities. And these Fabry-Perot cavities have, let's say, emission of, let's say, they are resonant. You have electric field that propagate through this space between the two mirrors, and if the electric field is resonant, you have an emission of peak light that let's say, and this peak light has a Lorentzian shape. So you will have, if you scan, say, the frequency of light versus let's say, scan the frequency, you will have more mirror emission. If we think to a stochastic gravitational wave background, a stochastic gravitational wave background will have many components of the frequency, and obviously in the frequency of the cavity, you will have a boost, let's say, of the photons, because this will sum coherently, and the mirrors have a finite reflectivity, so we can use it very narrow band. This is an example. So we might compute, let's say, a gravitational wave to photon conversion in the cavity. And when you compute the graviton to photon conversion in the cavity, when matches the resonance of the cavity, you can clearly see that there is that the flux inside the cavity is the transmission flux out the cavity is boosted by the factor F, where F is a parameter of the cavity that depends on reflectivity of the mirror, and this F can be tuned to have it higher possible. So, and the minimum sensitivity in amplitude is inversely proportional to the square root of F, where F is the thickness of the cavity. So in principle, having cavity and we can constrain better the magnitude, characteristic magnitude of the gravitational wave in that line. And the prospects for, let's say, ALPS II and JURA and IAXO are shown by this picture here. So this work, was done in collaboration with Mike Lewis, Damian, and John Paul and Hartmut Grote. Here I plot the sensitivity to stochastic gravitational wave background. So we have an improvement of orders of magnitude and narrow band in ALPS II and JURA, and here I have plotted also the nucleosynthesis limit to the fact that we observe some combination of in the stars, some combination of the elements, light elements, and here are also some plots with different masses of primordial black holes. As we can see, it's promising the fact that we are approaching to meaningful, let's say, sensitivities in order to exclude, to go below the nucleosynthesis limit, but still we are far. So what can be done is a question once we have, let's say, a system like ALPS II in order to improve the sensitivity. And one of the big questions is how to distinguish a noise from a noise. And here comes the idea of cross-correlation. So ALPS II has two cavities. One is for generation and one is for the conversion. We might use both of them. For example, one of the ideas might use both of them to as a gravitation to photon conversion and cross-correlate the signal. This is this test is a transistor edge detector, measures the energy. Actually, it doesn't measure the variation of the field, so we might have in time a signal, a rare signal that comes outside this conversion. So, and on the other side, let's say in a second cavity, we will have a shift between these two signals. And doing cross correlation by measuring the photons is possible, so, even if this is at high frequency. And in this way, you reduce the number, the background of counting of these two photodetectors, and you can correlate, let's say, the signal coming from a gravitational wave background and improve the sensitivity better. This is an idea where you improve the sensitivity by integrating 1 million of seconds. ALPS has also this potential to become gravitational Hertz experiments, since they shine laser through the magnetic field, and this laser has 150 kilowatt. One might think, what about the Gertsenshtein effect? So you generate gravitational wave on the first part of the cavity, and then you detect on the other side. So there is a paper on this idea by Kolosnitsky and Rodenko in 2015, and obviously I estimated the magnitude of let's say of gravitational wave produced by these powers, and they are more than 10 orders of magnitude of the sensitivity to, on the other side, sensitivity to gravitational wave and conversion to photon. So right now we are far away for having a Hertz experiment in gravitational wave, very far away, but still it has this conceptual design.
Aldo, do you have 5 minutes?
Yes, then I want to talk a little bit about the baby IAXO and IAXO, since they have this nice movable platform that can point. They can point towards the sun. Maybe with a little bit of modification, the platform can point somewhere in the sky. And where would be an interesting region to point? We know that in the center of the galaxy we have a big black hole, and we can, let's say, probe this 5-dimensional theory where the gravity is strong. So suppose that this is one of the plane where we live, the visible plane, and we have a trigger from LIGO that there is a black hole merging. This will excite, let's say, the tension between these two planes, and will generate a high frequency gravitational wave of order 10 to the 15 and so on. So depending on where happens this collision of black hole, you will have different strength of with some characteristic amplitude. If we could, let's say, point the baby IAXO, will have a sensitivity on gravitational wave calculated for the band 10 to the 17, 10 to the 18 of 10 to the minus 28. So it can constrain this theory or rule it out, or can make a constraint on this parameter where d is the distance between the planes and l is the curvature of the bulk. Let's say this is based on interferometry, Michelson interferometry that we are building here in Cardiff. It's not a magnetic conversion, but we are building 2 Michelson interferometers. And we will use cross correlation between them up to from 1 to 200 megahertz. This is in phase of building. Mainly is built for probing quantum spacetime. So we will vary the angle between the 2 arms in order to probe different theories of quantum spacetime. Can be used also for dark matter search and then a high frequency gravitational wave. Here, the novelty is that we will have a simple Michelson, power recycled Michelson with 10 kilowatt in Ejlli beam splitter. We will use squeeze light and optical mode cleaner to reduce the higher order mode content. And the sensitivity is better respect, for example, to shock noise level of Fermilab by 1 order of magnitude using 10 dB of squeezing. And since we have 2, we can cross-correlate them and improve the sensitivity by square root of time. Conclusion. So we saw that the axion search experiment set the first upper limit on stochastic ultra-high frequency gravitational wave background. The upgraded ALPS II, IAXO, baby IAXO can provide the infrastructure to improve the existing upper limits. With minor modification of these axion experiments, we could improve furthermore the sensitivity to the high frequency gravitational wave background. And I would say that this axion search experiment also are being identified as novel ultra high frequency gravitational wave detectors. And with this, thank you for your attention.
Thank you, Aldo. Perfectly in time, and we have some time for questions. Andreas, please go ahead.
Aldo, thank you very much for a nice talk. Is there any idea how to get, or do you have any estimate what we could learn, or what would be the sensitivity of ALPS II for coherent sources like primordial black hole mergers? So what you're seeing, so somehow maybe we could also give a limit from not observing something. We could also get a limit on the primordial black hole mergers, but somehow we have to be lucky that the thing goes along that the signal goes or is in the primordial black hole merger, that ALPS II is just pointing towards such a thing, or isn't it?
Yeah, thank you for this is interesting question, and just want to show this sensitivity to the dimensional amplitude. As you can see, with the decrease of the frequency, the amplitude becomes stronger and stronger, and
Yes.
we might need let's say detectors that can have sensitivity to single photon detector in this region. So detectors that are centered
Yes.
at
But this is still a stochastic background. But if I would now like to see, so to say, the signal from a primordial black hole merger within the galaxy or something like that. So,
yeah, this
or
is
in 1 kilometer. So because there are these estimates of the merging rate that there should be hundreds of per gigaparsec per volume of black holes, primordial black holes in the asteroid mass range or something like that. So if you don't have these things, so but
yeah, I haven't thought in such detail, but I would say something that we need pointing, since this is using the inverse Gertsenshtein effect. So if for some moment of the time is acquiring data and is pointing towards, let's say, that the gravitational wave is orthogonal to the magnetic field, obviously this could, and you have, let's say, some signal, maybe at high frequency, I don't know, but maybe we need the detectors at also a different frequency regime.
Okay, yeah.
Because if we put there and we see some signal, that could be a sign that there is some conversion. Yes, I will not exclude it, but it has the potential. ALPS II has this potential to be studied in this way, but maybe we need to say, suppose that we have a trigger from LIGO and we acquire also the ALPS II data at some frequency, we can see if there is a components at higher frequency of black hole merger. Not only seeing the waveform, but also components at high frequency.
Okay, thanks.
Francesco, please go ahead.
Yes, two quick questions. The first one is related to Carlos' talk. Can you comment on the possibility of using this idea in the gigahertz region? And then the second one, if you can comment on the phase coherence problem that you need to have in order to enhance the signal.
This is a question for Carlos, is that Francesco?
No, it's for you. It's related to
sorry.
stock.
So the detector at the gigahertz region, they suffer first of all because if you for number of photons per unit of time, if you have the same energy and you go at lower frequency, you will have a number of photons that is higher. So then the problem is that the phase coherence, because this process is a resonant process. You convert gravitational wave at the same into electromagnetic wave at the same frequency, and you have to take into account if there are processes that will, let's say, make decoherence of this conversion. And if you go to gigahertz region, you might need to use waveguides and the speed of propagation, let's say, of the electromagnetic wave in this waveguide might be different from the speed of propagation of the gravitational wave in vacuum. So this phase coherence, has to be taken into account, but becomes, let's say, very important if you go at the gigahertz region of frequency. If you are at this higher frequency, there is no problem. So we can assume that the process of converting gravitational wave into photon is a coherent process.
Thanks.
Okay, thanks again, Carlo and Aldo, sorry. And I think we can move to the next speaker, which is